In this second example, the directions tell us use the limit process to find the area of the region between the graph of the function and the y-axis over the given interval. Notice they're telling us how to do it and finding the area, not approximating the area, finding it, the exact area over the given interval. Notice that this is a function of y, therefore this interval is from the y coordinate 1 to the y coordinate 3, but this is still our interval on a to b. So if it's saying find the area of the region, that's the exact area. We're going to be using our limit process. Limit as the number of rectangles goes to infinity. The sum from the first rectangle to the nth rectangle of the areas, the width times the height. So remember, we need to work from the inside out, find the width and find the height first so that we can plug it in to the summation. So our width first, our delta x, that's our b minus a over n. We can use these values and just plug them in, 3 minus 1 over n, 2 over n. We can also find the f of c sub I by first finding the c sub I and plugging it into the f, and all of this can be done without a picture. However, it does make more sense with a picture. So let's practice graphing this function of y. You can think of this as x equals y squared plus 1, and we are looking from the y value 1 to the y value 3. This is a y to another y, the first y to the second y. So we want to be able to spread that out a little bit. So let's count 1, 2, 3 this way. And thinking about if we plug the y value 1 in here, 1 squared plus 1 is 2. However, plug 3 in, the upper limit of our interval in, 3 squared plus 1 is 10. So we need to go all the way up to 10. So we want to count differently on this axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that'll fit in there nicely. So plugging the y value 1 in, we get the x value 2. So plug the y value 1, we get the x value 2. Plug the y value of the upper limit in, 3, 3 squared plus 1, that's 10, so the x value 10. Let's also plug in the 2 into the y, 4 plus 1, that's 5. So the 2 goes with 1, 2, 3, 4, 5, like that. And then we can also think of this as a parabola that's opening to the right instead of up because it's y squared, and it's been shifted up 1 away from the origin, and by up we have to mean in this case in the x direction 1 unit. So the vertex would be here, and then it would be half of the parabola. We'd see the other half coming this way if we had room to graph all of it. And then we only want on this interval 1 to 3, so from 1 to 3, and remember that they said to find the area between the graph of the function and the y-axis. So here's the y-axis, and here's the graph of the function. So we want this area in there. That's the area that we're finding exactly. It also is helpful to have a picture because then once we get an answer, we can tell if it's a logical answer, if our numbers make sense. So let's continue and we'll check that at the end. So remember our c sub I is the starting value plus I amounts of delta x away from the starting value. So we're given the a as 1, so plug in 1 plus I, 2 over n is our delta x. We're going to need to use that. And we can't simplify this at all, so plug it now into the function to get our height. This is the x value, and this plugged in will give us the height. So it gets squared, and then plus 1. And we want to square this, and as we do, remember you have to think of it as multiplied to itself. And then plus 1 at the end, we don't want to forget that. So we'll FOIL this, 1 times 1, 1 times 2i over n, and then another one. So we have 4 of those. So I, 4 over n, and then we have the I times I, 2 over n times 2 over n, so that's I squared, 4 over n, and then the plus 1 at the end, and combine the like terms, so 2 plus I times 4 over n plus I squared times 4 over, oops, forgot the n squared. don't want to miss that. And it looks like we have all of that. So there's our height that we're going to plug in with our width. So let's go back up to our area and rewrite our limit. Sum from 1 to n. Our width is 2 over n. And our height is all of this. And then we want to simplify our sum. So notice that whether it's a function of y, a function of x, it's not really any different of a process. We find our delta x using the same b minus a over n. We find our c sub I by using the a plus I delta x, plugging it into the function. Whether it's x or I, it doesn't matter. Technically, this is change in y instead of change in x. So this is delta y instead of delta x, but it doesn't change what we're doing in the problem. So now let's use our properties, formulas. So if n is the upper limit, that means n is a constant. We can bring out any constant multiples and rewrite our limit. N approaches infinity, and we bring out the 2 over n, and we have the sum of the 2 plus I times 4 over n plus I squared times 4 over n squared. Sum is from 1 to n. Now we can use our summation to break up that expression. So again, we have the limit, 2 over n, and then the sum from 1 to n of each of these. Sum from 1 to n of I times 4 over n, and the sum from 1 to n of I squared times 4 over n squared. Then remember how we can take any constant multiples, pull them out of those summations. And again, let's rewrite what we have. Limit, n goes to infinity, 2 over n, sum from 1 to n of the constant 2, plus 4 over n, the sum from 1 to n of I, plus the sum from 1 to, our constant pulled out, then the sum from 1 to n of I squared. Now for this guy, we've got our formula, 2 times the upper limit. For this guy, we've got our formula, the sum of I, that becomes n plus 1 over 2, and then the sum of I squared that we used in the previous example, n plus 1 to n plus 1 over 6. Let's not forget all the other stuff that's around it, but we've successfully gotten rid of the summations, so that's helpful. We have a plus here, we have the constant multiple 4 over n, we have a plus here, and the constant multiple 4 over n squared. Now we want to simplify. So in this part, we've got those gone, we've got 2 goes into 4 2 times, we have a factor of n, we have 4 6 turns into 2/3, and remember we want to use as little effort as possible, so we're only going to simplify as much as we have to. At this point, we can now distribute the 2 over n into all parts here. So 2 over n, 2 over n, 2 over n, putting it into all those parts. Let me make myself a little bit more room. And 2 over n times 2n, the n's factor out and we're left with 4, plus 2 times 2 is 4 times n plus 1. 2 times 2 is 4 times n plus 1. The denominator has an n in it. Plus 2 times 2, again, is 4. And n plus 1, 2n plus 1 left in the numerator. Now denominator's n times an n times a 3. So that looks like 3n squared. Simplify a little bit more. Well, let's look at it like this. This 4 times n plus 1 becomes 4n plus 4. This, if we were to FOIL, this becomes 2n squared times 8. So that's 8n squared plus, and remember, the other terms are really going to be insignificant because we're only looking at the leading exponent, the degree, the highest exponent. That way we can use, when n goes to infinity, our degree shortcuts. So let's take the limit of each term. The limit of 4, no matter where n is going, just 4. Plus, here the degrees are the same, end of the first, so we do the leading coefficients, 4 over 1. Plus, last term, 8n squared over 3n squared. Again, the degrees are the same, so we just take the 8 thirds. There's our area, but of course, let's clean it up a little bit, simplify, make it a nice final answer. We have 4 plus 4 is 8, and 8 plus 2 and 2/3 makes 10 and 2/3. There is our final area. Now we talked about, does it make sense? Well, let's take our picture here, and if we were to say, estimate with one large rectangle like this, well, let's look at how many units is it wide? About 2 units wide. How many units is it long? That's about 1, 2, 3, 4, 5, 6, about 6 units long. And 2 times 6 is 12. So the area of this rectangle that I'm using to estimate is approximately 12. So does that look close to what we got? Yeah, it's not too far off. This was a really brief, quick estimation, but a way to check that we're not too far off.